Before we can really get into detail about substitution reactions, we have to review the idea of a Lewis acid and a Lewis base. So I'm going to start with a Lewis base, and you need to understand that a Lewis base is anything that can donate a pair of electrons. This is generally the definition of acids and bases that we as organic chemists like to think about because we're dealing with the movement of electrons. And so we often like to think about bases as Lewis bases, right? Because not necessarily they're accepting protons, that often happens, but more importantly, they're donating a pair of electrons. And we actually have a special name for a Lewis base, and it's called a nucleophile. So a nucleophile is a Lewis base. Those two terms are pretty much interchangeable. Now, what does that mean? It means that that something that can donate a pair of electrons, what is it donating it to? It's donating it to a nucleus of another atom. So it's seeking out a nucleus of another atom, hence the term nucleophile. Now, a Lewis acid is anything that can accept a pair of electrons. So Lewis acids have a much broader term than the typical Bronsted acid, which can donate a proton. So a Lewis acid is anything that can simply accept a pair of electrons. There are certainly Bronsted acids that are also Lewis acids, but there are many things in organic chemistry that aren't Bronsted acids but can still accept a pair of electrons. So because it can accept a pair of electrons, it's called an electrophile. So we have these two terms, nucleophile and electrophile. A nucleophile is a base, a Lewis base. An electrophile is a Lewis acid. And we need to get those terms straight before we really continue on to talking about substitution. So let's look at a few examples to kind of illustrate the idea of the Lewis acid-base approach. Here I have the hydroxide ion, has a negative charge on it, and I'm going to react it with HCl. So, in the past we've said, okay, the hydroxide is a Bronsted base, HCl is a Bronsted acid, because it donates a proton, and the Lewis base accepts a proton. But we can also think of the hydroxide ion as a Lewis base and the HCl as a Lewis acid. Why? Because the Lewis base donates a pair of electrons and the Lewis acid accepts a pair of electrons. Now, at this stage, we should know what's going to happen. We have a reaction that occurs where the Lewis base, the nucleophile, donates a pair of electrons to the Lewis acid, which is the electrophile. Now, in that process, we have a non-bonding pair of electrons being donated into the sigma star antibonding orbital of HCl. So in that process, a bond breaks because we're filling electrons into an antibonding orbital, and we get a reaction that ensues because the pair of electrons in that HCl bond go to the chlorine to make chloride. And so we produce water and chloride. But we can certainly think of this as a Lewis acid-base reaction. And oftentimes the nucleophile we're going to see has, a negative charge. Now, it's not always the case that it has a negative charge, but in general, Lewis bases have high electron density. But in essence, any substance, any atom that has a pair of electrons that are available can act as a Lewis base. For example, ammonia is a Lewis base. It has a pair of electrons on it, and we know that ammonia can react with hydrochloric acid. Hydrochloric acid would be the Lewis acid. So the ammonia Lewis base nucleophile is going to donate its electrons to the Lewis acid. And of course, in this particular case, since the Lewis acid is the same, we're we're donating electrons still to that sigma star antibonding orbital of HCl, and so a bond breaks. And the result is we get ammonium, the ammonium cation. And of course we get chloride ion. So here is a situation where the Lewis base isn't negative, but there is high electron density on the nitrogen. So one of the key things to get familiar with is recognizing when a when a compound is going to behave like a Lewis base. And in general, any atom that has a pair of electrons has the potential of behaving like a Lewis base and donating those electrons. And we'll start to get a feel as to, why are some atoms better at donating their pair of electrons than other atoms as we go along in the chapter. So here is an example. I'll show you a last example of a fluoride ion, which is a Lewis base. And it's going to react with BF3. Now BF3, notice, is a somewhat stable molecule, but the boron has only 6 electrons around it. And therefore, it has the potential of accepting another pair of electrons. And that's exactly what happens. The fluoride is a Lewis base. It's going to donate a pair of electrons. And the BF3 is a Lewis acid. It's going to accept a pair of electrons. Now, the end result is, well, what's happening? I'm actually BF3 is an sp2 hybridized atom, and so it has a p orbital. And what happens is the fluoride donates its pair of electrons into an empty p orbital. The LUMO is an empty p orbital. It's not an antibonding orbital, it's a p orbital. And therefore we don't break a bond in this particular case. We simply form a new bond, and we get BF4 minus. So this is a Lewis acid-base reaction, right? Where the nucleophile is attacking the electrophile. And it's important to understand where the electrons are going, if I'm forming a new bond or if I'm forming a bond and breaking a bond in the process. And that's why it's vital to understand the molecular orbital picture of what's going on. If we understand that if electrons are being donated into an antibonding orbital, then more than likely a bond's going to be breaking, right? Because you're populating an antibonding orbital and the bond order becomes 0. Or, like in the case of fluoride reacting with BF3, you're populating still a bonding orbital, a simple p orbital. And in that process, you create a new sigma bond. And of course, you're also creating a new sigma star bond that isn't populated with electrons. Now, another concept that we have to understand is that a reaction is exothermic, when the new bonding molecular orbital is more stable than the orbitals that created it. And it is endothermic if the new orbital is less stable than the orbitals that created it. Generally speaking, in organic chemistry, when we talk about a reaction taking place, we're typically talking about an exothermic reaction. So for example, if we think about the molecular orbital picture of it, we have a Lewis base that is the HOMO, right? It's providing the electrons. And then we have the Lewis acid that has the LUMO. It has the lowest unoccupied molecular orbital. So the Lewis base, HOMO, provides the electrons to the Lewis acid LUMO. They mix. The end result is 2 new molecular orbitals. One is a bonding, one is an antibonding. And of course, the 2 electrons then go into the bonding orbital, and we see that there is a net stabilization relative to the initial orbitals that mixed, right? And so this is an exothermic reaction. an exothermic reaction because the energy is going to be released to form a more stable product. Now, there are scenarios in which, um, especially if the energy between the HOMO and LUMO are very far apart, what you see is, again, the HOMO is supplying the electrons, but now when they mix, you actually end up getting two new orbitals that are higher in energy than one of the possible possible orbitals. So for example, the Lewis base, the HOMO of the Lewis base, right? And what you have here now is a molecular orbital diagram that looks something like this. It's kind of strange looking, right? But these certainly do happen, and it simply means that you have to add energy to the system in order for that reaction to even occur. So there's a net destabilization that happens. Do these happen often? Not very often, but they can happen if we supply enough heat, right? Enough heat to the system. So if we increase the temperature, we can get reactions like this to occur if the net destabilization isn't that great, okay? So one of the keys is to be able to recognize the Lewis base and the Lewis acid. So you need to work on, and if you're struggling with understanding, you get two reactants, which one's a Lewis base, which one's a Lewis acid. And in essence, from this moment forward, we can think of all reactions as the reaction of a Lewis base with a Lewis acid. You also need to be able to describe the HOMO and the LUMO orbitals that are interacting. This certainly can help you in recognizing when bonds form and when bonds break, right? So, for example, we already saw this reaction where you have ammonia reacting with hydrochloric acid. We know that the HOMO of this reaction is the electrons, the filled non-bonding sp3 orbital electrons of the nitrogen. So the HOMO orbital is that filled non-bonding sp3 orbital of the nitrogen. The LUMO is, we should know by now what the LUMO is. I've talked about it a few times. It's the empty sigma star antibonding orbital of HCl. And since it's an antibonding orbital, when we fill it with electrons, the bond between hydrogen and chlorine is going to break. And so we get a reaction that takes place, and you produce ammonium chloride, right? So that process in explaining, showing the curved arrows and explaining the HOMO and the LUMO molecular orbitals that are involved in this reaction start to paint a picture, right, of the reaction mechanism. Now, I won't, I say here the entire picture explains the reaction mechanism. We can go a step further in looking at an energy diagram of that, and the whole process itself then begins to explain the reaction mechanism. And that's what we're going to be exploring throughout this chapter.